Okay, so we are going over the indefinite integral in section 5.2. Common theme in math is to go backwards. You first learn to add, then subtract. You then learn to multiply and then divide. You learn to square and then square root. You learn to exponential functions and then logarithmic functions. And so in math, very common theme is we like to work backwards. So that's what we're doing in section 5.2. We're working backwards. So pause the video and find a function whose derivative is x to the fourth. That is, find capital F of x such that f prime of x is equal to x to the fourth. And so this is just by inspection and experience. There's no, you don't need any training for this. You've done enough derivatives that you should know that if I want to end up with x to the fourth, then f of x should have been a power function. And when we take the derivative of a power function, we're going to bring down the exponent and take one away from the exponent. So since we want to end up with an exponent of 4, then it makes sense that this should have been an exponent of 5. But when I bring that down, I won't have a, I'll get this extra factor of 5. So to compensate for that extra factor of 5, we can put this 5 down here. That way when I bring it down, it cancels out. You could always check your answer. F prime of x, following the rule for power function, bring down the exponent, take one away from the exponent. That constant of 1/5 just stays there. They then cancel out, and we end up with x to the fourth. So if you printed the class notes, you should cover up the class notes so that you can find these antiderivatives on your own without writing them down. So cover them up, guess, and then make sure that you're right. So some vocabulary. A function f is called an antiderivative of a function little f on a given open interval if f prime of x is equal to f of x for all x in the interval. So an antiderivative is just a function that gives you the derivative of the function you were given. Right? So that's all an antiderivative is. Now, one of the things you should ask yourself, or one of the common questions is, well, is it unique? Is there more than one antiderivative? And it turns out that there is more than one, but they all kind of look the same. And so we kind of talked about this in section 4.8 when we were dealing with the mean value theorem. But here it's phrased slightly different. If f of x is any antiderivative of f of x on an open interval, then for any constant c, the function f of x plus c is also an antiderivative on that interval. That should be obvious because the derivative of the constant is 0. So if f is an antiderivative, then the derivative of f of x plus c is also little f of x. So adding the c gives you a different function that also has the same derivative. But moreover, each antiderivative of f of x on the interval can be expressed in the form f of x plus c by choosing the constant c appropriately. Right? So the antiderivative is unique up to a constant. So it could be plus or minus some constant is basically the gist of that. So the indefinite integral. The process of finding antiderivatives is called antidifferentiation or integration. These are just words that we use. Thus, if you know that the derivative of capital F of x is little f of x, then integrating or antidifferentiating the function f of x produces an antiderivative of the form f of x plus c. To emphasize this process, equation 1 is recast using integration notation. Right, so part of the class is for you to get comfortable with the notation. And so the way you read this is the indefinite integral of f of x dx, or with respect to x, is equal to capital F of x plus c. So up here you're told that the derivative of f of x is little f of x, or the derivative of capital F of x is little f of x. And so then over here you're being asked find a function whose derivative is little f of x. And since you already knew up here big f of x satisfied that, well, then the answer is f of x plus c, where c is understood to represent an arbitrary constant. It is important to note that 1 and 2 are just different notations to express the same fact, different ways of saying the same thing. The expression, the indefinite integral of f of x dx is called an indefinite integral. The adjective indefinite emphasizes that the result of antidifferentiation is a generic function described only up to a constant term. The elongated s that appears on the left side of 2 is called an integral sign. The function f of x is called the integrand, and the constant c is called the constant of integration. The differential symbol dx in the differentiation and anti-differentiation operations. So this is the one in the differentiation. This is the anti-differentiation. They both have a dx. Serves to identify the independent variable. So that tells you what variable is the independent variable, the input variable. If an independent variable other than x is used, say t, then the notation must be adjusted appropriately. So we've already differentiated with respect to other variables other than x. We have ddt'd, and we will integrate with other variables other than x. So then in the integral symbol, the dx gets replaced with dt. Just notation, no big deal. Okay, so pause the video and take a moment and do each of these. So each of these is just a power function. And so then, again, this is just asking, what do I take the derivative of to get x to the third? And again, if we want to end up with an x to the third, a power function, then we should start with a power function. And since we're going to take one away from the exponent when we take the derivative, well, then we should start with one more. So we should start with an x to the fourth. But when we bring down the 4 and there's no 4 in the function that we were given, we want to cancel that out, right? Same, each one of these is exactly the same. Since we have a power function, x to the fifth, we want to take the derivative of it and end up with x to the fifth. So then we should start with an exponent of 6, and we divide by the 6. Same thing, x to the eighth. We needed to have started with x to the ninth and then divide by the 9. Oh, I'm forgetting. So this symbol always is asking for the most general antiderivative, and so each one of these should have a plus c. If on your homework or quiz you forget the plus c, then it's a point off. And so then here we have a general formula, right? Anytime we see a power function, no need, not very difficult. We're just going to add 1 to the exponent and divide by the new exponent. This way, when I take the derivative, don't forget the plus c. When I take the derivative, I will bring that down. The n plus 1s will cancel out, take 1 away, and I'll just end up with my x to the n. And that's another key thing here. When you're finding antiderivatives, you could always check your answer by taking the derivative and making sure that it matches. And so here's the result. No work to show on power functions. You find the antiderivative by adding 1 to the exponent, dividing by the exponent, and don't forget the plus c. That's what this says. Okay, so we're not going to have product rules or quotient rules or anything like that. So the only thing you know how to take the antiderivative of right now is a power function. And so then there's some algebra that needs to be done here to be able to do this problem. We need to be able to write the integrand as a power function. But again, what we have here is x to the fourth over x to the 1/3. And using the rules of exponents, we can subtract the exponents. We can take the 4 and subtract the 1/3. And if you want, you can use the calculator to do that. 4 minus 1/3, math 1, is 11/3. If you want to get better at fractions, you should do that on paper by hand. But we get this 11/3 by subtracting the exponent. So this integral that we were given can be rewritten as the antiderivative of x to the 11/3 dx. This is still just a power function, right? It's just x raised to a power. So the antiderivative is to add 1. So you end up with an exponent of 11/3 plus 3 more thirds is 14/3. And then rather than dividing by this, since we are since it's a fraction, we can multiply by the reciprocal. 3 divided by 14. And you see now, don't forget the plus c, that if I were to take the derivative of this, when I bring down the exponent, the 14/3 would cancel out the 3/14, take 1 away, and I would get the 11/3. And the derivative of that constant would be 0. This is not a power function. So just, again, cover up the class notes so that you don't see the answer. Just ask yourself, what do I take the derivative of to get the cosine of x? So this is going backwards, and it gets a little confusing at first because you've only been going forwards and now you're being asked to go backwards. But you should know that the derivative of the sine is the cosine. So then what do I take the derivative of to get the cosine? The sine of x plus c. You can check it by taking the derivative. The derivative of the sine is the cosine. You should have that memorized, and the derivative of the constant is 0, so we are good. But now, anytime you see the you're being asked to find the antiderivative of the cosine of x, the answer is the sine of x. And so that's the result. No work to show. You just have to memorize this. The antiderivative of the cosine of x is the sine of x, and that's because the derivative of the sine of x is the cosine of x. This is the one that throws people off. Find the antiderivative of the sine of x. Well, if you guess that it's the cosine of x, then you should check it. When I take the derivative of the cosine, I get the negative sign. Not what I want. I just want sine. I'm off by a factor of -1. So if I include a factor of -1, then when I take the derivative of the cosine, I get the negative sign times the -1. I will get my positive sign. So this is the answer. You should, instead of just watching the video and watch me doing this, you should pause it after every one of these, because you should be able to do these on your own, right? You just want to go through them and then get comfortable with it. So here's your result. Anytime you want to find the antiderivative of the sine of x, the answer is the negative cosine of x plus c. Okay, so again, all you're being asked to do here is ask yourself, what do I take the derivative of to get the secant squared? And so then you should have these memorized, burned in your brain, that the derivative of the tangent is the secant squared. So then that means then that what did I take the derivative of to get the secant squared? That is the tangent of x plus c. What do I take the derivative of to get the secant tangent? You should have burned in your brain that the derivative of the secant is the secant of x tangent of x. So then what did I take the derivative of to get the secant of x tangent of x? The secant of x plus c. It's just off of memory. There's no work to do. So every time you take the antiderivative of the secant of x tangent of x, the answer is the secant of x plus c. What do I take the derivative of to get e to the x? Well, you should know that the derivative of e to the x is e to the x. So then what did I take the derivative of to get e to the x? E to the x plus c. And so the antiderivative of e to the x is e to the x plus c. Okay. Now this does look like a power function. But if you looked at this as x to the -1 dx, then when you add 1 to the exponent, you'll get x to the 0, and you divide by the new exponent 0. Now you're dividing by 0. That doesn't work, right? You're not allowed to divide by 0. Still not allowed to divide by 0. So this is the only power function that the power rule doesn't work, right? And so now again, you're asking yourself, what did I take the derivative of to end up with 1 over x? And so then you should know that the derivative of the natural log is 1 over x. So then the antiderivative of 1 over x is the natural log of x plus c. It turns out that we went over this, that if you took the derivative of the natural log of the absolute value of x, you also got 1 over x. So since we want the most general antiderivative, we're going to use as the antiderivative of 1 over x the natural log of the absolute value of x plus c. So as you're going through your homework, here are the formulas. Now, when you just see the antiderivative of dx, much like in algebra, we don't write a 1, we just write dx, but it's, asking what do you take the derivative of to get 1? And of course, that's just x plus c. For the power functions, what do you take the derivative of to get x to the r? Well, you figure that out by adding 1 to the exponent and dividing by the exponent. But this doesn't work if your r is 1. So it works for all r's except r cannot be negative 1. The antiderivative of the cosine of x is the sine of x. The antiderivative of the sine of x is the negative cosine of x. The antiderivative of the secant squared is the tangent of x. The antiderivative of the cosecant squared is the negative cotangent of x. The antiderivative of the secant x tangent x is the secant of x. The antiderivative of the cosecant of x cotangent of x is the negative cosecant of x plus c. The antiderivative of e to the x dx is e to the x plus c. We're not going to use this a ton in this class, and it won't show up on your homework. I'm sorry, it won't show up on your exams or quizzes. But if you have a power function, exponential function where the base is not e, then your antiderivative is b to the x divided by the natural log of b. That might show up on your homework. The antiderivative of 1 over x is the natural log of the absolute value of x. We went over that the derivative of the inverse tangent was 1 over 1 plus x squared. So the antiderivative of 1 over 1 plus x squared is the inverse tangent of x. Same thing with the inverse sine and inverse secant. Now, we went over that if you're taking the derivative of a constant times a function, then you can just take the derivative of the function and then multiply times the constant. We also went over that if you're taking the derivative of a sum of two functions, or difference, then you can just take the derivative of the first function and add it or subtract it to the derivative of the second function. And so then, since antidifferentiation is related to differentiation, the same rules should apply, and that turns out to be true. So suppose that capital F of x and capital G of x are antiderivatives of f of x and g of x, respectively, and that c is a constant. Then a constant factor can be moved through an integral sign. That is, when you see just a constant times a function you already know how to find the antiderivative of, you can just find the antiderivative of the function and then multiply it by the constant. That's what that is saying. When you're looking at a sum of two functions, you can just find the antiderivative of the first function and add it with the antiderivative of the second function. Same thing for the difference. And again, that works because those are the rules we learned about differentiation and how they work. So when you see something like this, I don't need to see all this work. I really don't want to see all this work, but let me just show you how that theorem applies to something like this, right? So then this then can be done as two different integrals. The integral of 3x to the 5th dx plus the integral of 4x dx. And then, because of these constants, we can just bring these constants out and multiply and take 3 times the antiderivative of x to the 5th dx and add it with 4 times the antiderivative of x dx. And then this is now just a power function that we have a formula for. So we can just add 1 to the exponent, x to the 6th, divide by the exponent, but then we have the 3 that was out in front, plus c1. And then for the x, the exponent is 1. We add 1 to the exponent, x squared, divide by the exponent 2, and then we have the 4 out in front, plus c2. But now this c1 and this c2, since those were arbitrary constants, we can just combine them into one constant. We can reduce this down to x to the 6th divided by 2 and 2x squared. And we can combine the two constants into one constant because they're arbitrary constants. So instead of running around with c1 plus c2, we can just say plus c. Now, if that helps you and makes it more clear for you, that's fine. That's great. But here's how I expect you to do the problem, right? So sooner or later, you will do the problem like this, right? I have a sum of two functions, so I just find the antiderivative of this one. This one is a power function, so I'm just going to add 1 to the exponent. Sorry about that. I'm going to add 1 to the exponent, divide by the exponent, and then multiply it by 3. Same thing for the second one. Add 1 to the exponent, divide by the exponent, and multiply it by 2. And then I have to add my constant. And then this becomes x to the 6th over 2 plus 2x squared plus c. Same answer, a lot less work. Okay, so again, we can ignore the constant. The antiderivative of e to the x is e to the x, and multiplied by 6 plus c. Okay, so you should be trying these on your own. Don't just sit there watching this video. That's going to get old quick. But so we just have four terms. Each term is a power function. So then we just add 1 to the exponent, divide by the exponent, times the 6. Add 1 to the exponent, divide by the exponent, times the 4. Add 1 to the exponent, divide by the exponent, times the 8. And you can look at this as x to the 0, or you can just ask yourself, what do I take the derivative of to get just 5? And that would have been 5x. And then plus c. Clean that up. 6 over 4 reduces down to 3/2. X to the 4th minus 4/3 x cubed plus 4 x squared minus 5x plus c. Please don't make up any rules. We don't have rules for powers. We don't have rules for products. We don't have, all we have is rules for constants times a function that we know what the antiderivative is, rules for sums and difference of functions that we know what the antiderivative is. With this exponent right here, we don't know how to deal with that, right? You can't just start adding 1 to the exponent and dividing by the exponent because this is not a basic power function. The base is not just y, it's 2 plus y squared. And so then the very first thing that you do with this is apply some algebra, right? 2 plus y squared is you just square that out. 4 plus 4y squared plus y to the fourth. And now it's all squared out. Now we can find the antiderivative easy. Find the antiderivative of each piece. The antiderivative of 4 is 4y. The antiderivative of 4y squared is 4y cubed divided by 3. Add 1 to the exponent. Divide by the exponent plus c. Again, we have a product. So there's no product rule. All we're doing in this section is we're making the integrand that we are given look like sums of integrands that we know, right? And so here, if we distribute the cosecant, we end up with cosecant times sine is 1. And then cosecant times cotangent, we don't have to do anything with because that is on our table. The antiderivative of 1 is just x. And the derivative of the secant is the secant tangent. So the derivative of the cosecant is the negative cosecant cotangent, is the way I have those memorized. And so then the antiderivative of the cosecant cotangent is the negative cosecant of x plus c. You're just asking yourself, what do I take the derivative of to get cosecant cotangent? You should have memorized that the derivative of the cosecant is the negative cosecant cotangent. Since you want to end up with a positive, just throw on an extra negative on there. Okay, what's the whole point of the plus c? An antiderivative is unique up to a constant, and so then we can figure out what that constant is if we know an input-output pair, and that's called an initial value problem. So here we know that dy dt, the derivative, is secant squared of t minus the sine of t. And we know that for the original function, so we know the derivative, we know that for the derivative function, for the original function, when we put in pi over 4, we got 1. And so then if this is the derivative, you're asking yourself, what was the original function? What did I take the derivative of to end up with secant squared? The derivative of the tangent is secant squared. So the first term must have been tangent. And everything's in t, so it's the tangent of t. And then if I want to end up with minus sine of t, then I could have had a plus cosine of t. But we don't know what that constant was. Any constant I put after that would still give me the same derivative, so I have the plus c. And so then the plus c is so that you can fit your specific curve to a point. And so now we can figure out what the c is by being given this input-output pair. And if I put in pi over 4 for t, my y value is 1. So I end up with this equation, that 1 is equal to the tangent of pi over 4 plus the cosine of pi over 4 plus c. So now I have an equation with only one variable, c, and I can solve for it. So 1 is equal to 1 plus root 2 over 2 plus c. So then c is equal to negative the square root of 2 over 2. So then, finally, I can figure out what my exact equation was. It was y was equal to the tangent of t plus the cosine of t minus the square root of 2 over 2. And this function here satisfies the fact that when I take the derivative of this function, I get this. And when I plug in pi over 4 into this function, I get this. That's called an initial value problem, and that is the solution. Okay, solve the initial value problem. So again, we're looking for a function whose derivative is x squared times the square root of x cubed. Again, since we don't know how to deal with products, which is what we have there, we use some algebra to write it so that it's not a product, so that it's just a power function. And that is just x squared times x to the 3 halves. 4 halves and 3 halves is 7 halves. So that's x to the 7 halves. So I took the derivative and got x to the 7 halves. That's what that says. What did I start with? Well, I had a power function. I took one away and ended up with 7 halves, so I must have started with a power of 9 halves. And since I don't have anything left, I had to have had a constant of 2/9 out in front, so that when I bring it down, that goes away, plus c. But here, you're given an input-output pair that allows you to figure out what c is. If c is 0, y is 0. I'm sorry, if x is 0, y is 0. And so when you plug that in, you'll get 0 equals 0 plus c. So c equals 0. So the solution to your initial value problem is a function that satisfies everything you're being told. And so your function is 2/9 x to the 9 halves. And this function, when you put in 0, you get out 0. And when you take the derivative, you end up with that. Okay. So a particle moves along an s-axis with the position function s equals s of t and velocity function v of t equals s prime of t. Use the given information to find s of t. Okay. So again, in the last chapter, we were able to start with the position function and take the derivative and come up with the velocity function, take the derivative of that, and come out with the acceleration function. And so then in this section, we started talking about antiderivatives, and you might have been asking why. Well, what if we knew the velocity function? Then we could work backwards to come up with the position function, which is what we're doing, right? So again, if you wanted to show some work here, your position function is just the antiderivative of the velocity function. Which in this case is the antiderivative of the cosine of t dt, which is the sine of t plus c. But the plus c, what it does here is it tells us, it allows us to have different starting points, right? And so then we can only figure out the plus c or the value of c if we are given an input-output pair, which we are. If we put in 0, we want to get out 2. So we get 2 is my output, 0 is my input. And you can see then that c has to equal 2 because the sine of 0 is 0. So c has to equal 2. And then that means that your position function is the sine of t plus 2. Okay. So find an equation of the curve that satisfies the given conditions. At each point xy on the curve, the slope is x plus 1 squared, and the curve passes through the point -2, 8. So at each point xy on the curve, the slope is x plus 1 squared. So the slope, they mean the slope of the tangent line. And what gives us the slope of the tangent line? The derivative does. So what we're being told here is that the derivative, dy dx, is given to us by this formula, x plus 1 squared, which is not very useful as far as finding the antiderivative, so we should expand that. X squared plus 2x plus 1. And so then if we just work backwards, what did I take the derivative of to get this? So y is the antiderivative of x squared plus 2x plus 1 dx. And again, these are just power functions, so you just end up with x cubed over 3 plus x squared over 2 times 2 plus x plus c. But we need to figure out the value of c, and we know that when I put in -2 for x, I get 8 for y. So then I get 8 is equal to -8 thirds. The 2's cancel out here. Plus 4 minus 2 plus c. So the -8 thirds plus 4 minus 2 works out to be -2 thirds. And then if you add 2 thirds to both sides, you get 26 thirds. Find an equation. So we're not done yet. You need to write down the equation. The equation is y equals x cubed over 3 plus x squared plus x plus 26 over 3. And that is what we're looking for. Okay. So this is your homework for section 5.2. I will also be uploading section 5.3 this week. And on Tuesday during class time, which starts at 2:30, I will host a conference to go over any questions that you might have over any of this. And so then that's how we're going to handle this now. Well, stay safe. Have a good day.